So we have a lovely test here. Math 1650, that's what we call it locally, but probably better known as Calculus 1. And this is the first test in Calculus 1. It means we got some basics, ideas, particularly limits, and some derivatives. It's going to be a lot of fun. Now this one comes with a formula sheet. And so know your formulas. And we're going to probably do a little bit with our average rate of change, our definition of derivative showing up here with instantaneous rate of change, a little bit of limits there. It's going to be good. It's going to be fun. And of course, as always, if we're going to take a test, we want to make sure we put our name on it so that we get the credit. All right. Well, lots to look forward to, 6 multiple choice, and 4 workout. So let's begin. Number 1. The average rate of change of the function, g of x, which is equal to x squared minus ax plus 1 on the interval from 1 to 3 is 5. Find a. All right, so we know the average rate of change, and we're trying to figure out a. Now, we just pulled up the formula sheet, and hey, wouldn't you know it, that's one of our formulas for average rate of change right there. You know, AROC versus IROC. All right, so AROC. So what's happening? Well, we have that the average rate of change, we'll write it down for reference. That's f of b minus f of, and I hate to use a because they're using the symbol a. I'll switch to big letters. F of capital B minus capital A, B minus capital A. All right. So here, this is our interval a, b. So we say, all right, our average rate of change is 5, and that's equal to, what happens when we plug in 3, subtract, what happens when we plug in 1, divide by 3 minus 1. Okay, that's what we were told. Average rate of change from 1 to 3 is 5. That's that formula. Okay, well, we can now plug in. And I've been using F. I should use G. All right, no problem. Switch to G's. It's our test. We can do what we want, right? Especially with multiple choice. We're not being graded on notation. We just need to make sure we get the right answer. Okay, so we plug in 3, and we're going to get 9 minus 3a plus 1. Subtract, plug in 1. 1 minus a plus 1, all over 2. All right, well, let's get rid of our fractions right away. So I'm going to multiply through both sides by 2, so we get 10 is equal to, and over here we're going to get 10 minus 3a, that's this first one. And here we're going to subtract, there's 2, and minus a makes plus a. All right, well, okay, good. 10s cancel. We can move the a's across, and we'll get 3a minus a makes 2a equals minus 2. And we get that a equals negative 1. All right. Woohoo! And that's an option. Nice. Nice. Does that mean we didn't make a mistake? No. But it means probably we're on the right track. And so what's the thing? Just know the formula. When you see average rate of change, know what that corresponds to. And I'm not a big fan of them using little a here just because that shows up meaning something different. But that's okay. I will say, in math, there's lots of bad notation out there. So that's all right. We love our math teachers. They're nice people. They're nice people. Yeah. All right, let's move on to number 2. Let f of x equal x cubed plus 2x minus 1. Find the points at which the tangent line to the graph of f of x is perpendicular to the line y equals minus x over 14 plus 1. All right, now this requires us to know a little bit of geometry in some sense, right? We see perpendicular. And now we say, okay, and not only perpendicular to a line. When are two lines perpendicular? Well, the answer is the slopes need to be negative reciprocals. So negative reciprocals of the slopes. All right, that's a lot of big words for just saying you need to multiply by negative and flip it upside down. So currently our slope, negative 1 over 14, right? We read off the coefficient of x. So that says we want to make it a negative. So minus minus makes a plus. Flip it. So this is our goal. We want to have a slope of 14. That's what we want. Okay, now, how do we find tangent lines with a particular slope? Well, we say, well, what is interpreted as a tangent line of a slope? And that's the instantaneous rate of change, or the derivative. So we say, aha, this is our great aha, we need to set f prime of x equal 14 and solve. All right, well, so what is f prime of x? That would be, take the derivative of x cubed, 3x squared. Derivative of 2x plus 2 equals 14. We can subtract 2, so we get 3x squared equals 12. Divide by 3, that gets us x squared equals 4, and that gets us to x equals plus or minus 2. So that says, hey, you know what? There are going to be two locations where this happens. One is at positive 2, and one is at negative 2. And so I say, well, that's not a positive 2 or a negative 2, so that's out, that's out, that's out. And, well, this has a 2, 11. Well, this has 2, 11, and negative 2, negative 13. And so it says you have to find the points. So the answer has to be D. Now, technically, we should double check. And why should we double check? Well, we should check the y coordinates. And so plug in positive 2, you'll get 8 plus 4 minus 1 is 11. Plug in negative 2, minus 8 minus 4 minus 1 is negative 13. I don't know why they really insisted on writing the y coordinates on this problem. It's a choice. Everyone can make choices. But there we go. There we go. All right, so that's number 2. Number 3. Choose the correct statement concerning the function. We have f of x is 5x squared plus 5x minus 1, and over x squared plus x minus 6. And we look at this and say, okay, so this is polynomial over polynomial. And looking ahead, we sort of skim. We say, oh, we see things about asymptotes and continuity. Say, okay, well, certainly there's a potential for asymptotes. There's two kinds. There's vertical asymptotes and there's horizontal asymptotes. Let's put on our vertical asymptotes hat first. And for that, we say, well, is there a potential for dividing by 0? And for that, we say, well, can we factor the denominator? And we look at this and say, yeah, that looks like it's factorable. Can we think of two things that multiply to give us negative 6, but would add to give us a positive 1? Well, I can think of two things. X plus 3, x minus 2. Right? We can check it out. X squared minus 2x plus 3x. That's x and minus 6. All right. So that's good. Now, does that mean we have asymptotes where we have zeros downstairs? Not necessarily, because they could have done something sneaky and said, oh, maybe this top factors and you get cancellation. So the only thing we really kind of have to worry about right now is to say, well, what are our potential places that we have problems? At negative 3 and at positive 2. And just check. If you plug in negative 3, do you get 0? We get 5 times 9, which is 45, minus 15, minus... No, that's not 0. How about 5 times 4? It's 20 plus 10, minus 1. No, that's not 0. Okay, so there's no common factors for the upstairs and downstairs. That's actually good news for us. Like, yay, us. So we're not going to get cancellation. Okay, so at this point, we can say, okay, so we have to have vertical asymptotes have to happen at x equals negative 3 and x equals positive 2. Okay, so that's not good. B is possible. It's not continuous because we have asymptotes. That's not good. Okay, and E is possible. All right, so we've ruled out A, C, and D. Now, what distinguishes the last two? Well, this one says horizontal asymptote at 5, no horizontal asymptote. Now, how do you do horizontal asymptote? Well, for that, here's how I like to do it. Now, I don't know how you like to do it, but here's how I like to do it. I like to say, okay, when I'm thinking horizontal, I'm thinking big, in the long run, like way over there and way over there, like, what's going on? And for that, I say, what's driving the growth? In polynomials, it's the highest term, the highest power. So for very large values of x, it's like you're covering up those smaller pieces. And we say, well, it's behaving like 5x squared upstairs and x squared downstairs. In other words, it's behaving like 5. In particular, since the powers agree, then we take the ratio of the coefficients. If the powers didn't agree, then if the higher power was downstairs, it'd be 0. If the higher power was upstairs, well, we wouldn't have any horizontal asymptote. We say, but hey, look, it's behaving like 5. So leading coefficients tells us, and we'll even write this down, not that we have to, I mean, it's multiple choice, but leading coefficients, that tells us that y equals 5 is horizontal asymptote. And so that rules out E, but we match. Oh, sorry, here we are. I'm up here, 5. So it's B. That's our vertical asymptotes and right horizontal asymptotes. All right, good. Our limits with infinity, right? Yeah, that's something we talked about one day, so we better have it somewhere. Number 4. If the function f of x defined below is continuous at x equals 0, what is the value of a? And, well, what can we say? We have a plus 3 secant 6x, 1 minus cosine 4x over 4x squared. All right, well, what does it mean? It means that when we're approaching from the two sides, we don't want this, we don't want that, we want them to agree. Okay? So, our goal, we say, look, the limit as we approach from below, and we're approaching 0, that's our point that we're interested in, of f of x, better match the limit as we approach from above of f of x. Now, from below, this is what? Limit as x approaches 0 from below of a plus 3 secant 6x. Now, the rule of thumb is, if you can plug in and there's no problems, life is good. Life is wonderful. Now, can you just plug in? Yeah, because what do you get? You get secant of 0. Secant of 0 is fine. Secant of 0 is 1. And you say, oh, okay, so just plug in. So we're plugging in, and we get a plus 3. And we're like, cool. So we get a plus 3 has to equal something. Now, what's that something? All right. Here we're going to do a little bit of work. I can already tell. Now, there's going to be better ways later on. And there's these really cool things. We're going to be putting on our little French hats. And we're going to be going, but that's not us. That's not yet. So we have to think about what technology do we have. And you might say, well, why are you making all of this fuss? Well, because now what happens? When you plug in 0, right here we just plugged in 0, and we're like, we got a number. A plus 3, life is good. When you plug in 0 now, you get 0 upstairs and 0 downstairs. And 0 over 0 is more work. More work. Okay, so there's more work that lays ahead for us. So we got to think about how do we handle that. And so there's a couple of things we can look for. And we're saying, okay, not a lot we can do with that 4x squared downstairs. Upstairs we have a 1 minus cosine of something. And we start skimming, we have all this trig stuff. can we find anything in our trig stuff that looks like a 1 minus cosine? And lo and behold, there is. And okay, so I think this is what they wanted us to see. This part right here, that 1 minus cosine 2 theta is sine squared theta. And so we say, okay, so a 1 minus cosine, what if we replace theta by 2x? Then what we get is the following. We make a little note. Multiply the 2 across. 1 minus cosine of 4x would be equal to 2 sine squared of 2x. Okay, all right. All right, so I'm just putting in theta equals 2x, so I get that 4x. So, by trigonometry, this becomes the limit, as x approaches 0 from above, of 2 sine squared of 2x over 4x squared. And at this point, you're like, you still have the same problem, Steve. There's still 0 over 0, man. How are we going to recover? But it's not just any 0 over 0. And in fact, I should have pointed this out earlier. We have this really cool fact. When we see a limit which has both trigonometry and polynomials, and we're getting 0 over 0, almost always we come back to this fact, that sine of blah over blah is 1. Now, they use the symbol theta instead of blah, but it really can be anything. And so we're like, oh, let's try to use this. So if what's underneath matches what's on the inside of sine, then it goes to 1. So we say, okay, well, the inside is 2x. I want the downstairs to look like 2x. And we're like, well, wait a second. It kind of really does, right? So we can think of this as sine of 2x over 2x squared. All right, then we get our sine squared of 2x, and we get 4x squared. And now the great aha is that this part goes to 1. So the whole thing is 2. So what's our punchline? We said this part, if we follow it through, equals that part. Okay, so a plus 3 equals 2. Subtract 1. A is minus 1. Sorry, I said subtract 1. Subtract 3. A is minus 1. So our answer is D. Whew. Okay. All right, I think this one definitely, you kind of like needed to know that step. But you should recognize, right? If you see trig and polynomials, you're like, I want sine over, sine of blah over blah. That's my goal. So how can I make my trig look like sine? And so that was a big clue about the way we're going to approach this one. There are other ways you can do it, but we only need one that works. And that's good enough for now. All right, let's move on to number 5. Suppose the function f of x has a jump discontinuity at x equals 3. Now, to be clear, that means it's doing this, right? From the two sides, it's approaching different values. The function is g of x is defined by looking at the square of f of x. Which of the following 3 statements are true? And statement 1, it says g of x maybe is continuous at x equals 3. So somehow we were misaligned, but when you square it, we're aligned. Okay, could that work? Well, sure, that could work. We could do what? Well, we could, from one side, we could say approach positive 1, and from the other side, we could approach negative 1. And then what happens? Well, instead of doing this, when you square, it does that. All right. So yeah, that can happen. Now notice, it doesn't say it will be, it says maybe. So it's possible. G of x may have a removable discontinuity at x equals 3. Now here's the thing. When we talk about jumps, right, they're misaligned, but we don't pay attention to what actually happens at the point. See, now when I drew this picture for the first one, I said, I'm approaching what I think I should on one side, but not for the other side. But we could do something like this, where we say we approach 1, and then here's negative 1. And now what happens? We're still doing that, right? But in the middle does something different. So when we square, we now, from both sides, we were thinking 1, but we still think 0 at 0. So now it's removable. So yeah, that could happen. Again, it's a may, not a will. And it says, oh, g of x may still have a jump discontinuity. Maybe squaring doesn't fix it. Like, yeah, that could happen. You could have something like here, I'll go up here to 2, and then down here, I'll still be like negative 1. So it's like I have a discontinuity, but now I have a different discontinuity. That's a jump. So yeah, that can happen. Okay, so what does that mean? Well, all these things can happen. And so we say, okay, well, great. Any of them can happen. So all of the statements are true. So this one is sort of an interesting one. It's basically saying, do you understand what squaring can do? And it's sort of saying, well, you're sort of more or less, it's like, oh, if I have one behavior up and one behavior down, we're bringing the down behavior up. It's like, well, I might be able to align it. They might not align still, or those kinds of things going on. It's a fun question. It's but one which you kind of have to understand what's going on. But that's okay. Our goal is understanding. Our goal is understanding. Our goal is to think about things. So, be careful. Sometimes we try to think of just very simple situations, but just try small perturbations. What about this? What about that? What does squaring do? It's like, oh, it makes everything positive. Oh, so what if one thing was negative, one thing was positive? Okay, what can I have happen? All right, number 6. Suppose that f of x is twice differentiable. That just means we can take 2 derivatives. And h of x is x squared f of 2x. Suppose that, and we have information about f of 2, f prime of 2, and f double prime of 2. Find h double prime of 1. Now we have 2 things going on here. One thing is we have a 2 on the inside, right? It's not just x, it's 2x. So what are we going to need to handle 2x? We're going to need the chain rule. The other thing going on is we have this x squared times. So we're going to have a product. So this is going to test us on 2 ideas. We're going to need to be able to do product rule, and we're going to have to do chain rule. Okay, so double the fun. Well, that's okay. We'll just take things slowly. And, we'll write down h of x for reference, x squared f of 2x. H prime. Okay, product rule. I start by saying get rid of the first, so that would be 2x. Leave the second alone. Plus, now take the first, as is, leave it alone, times the dirt of the second. So that's f prime of 2x, and then chain rule, times the dirt of the inside, 2. The way I like to remember the product rule is every piece gets its turn. All right? It's like, okay, x squared, you get a turn, but everything else stays as is. F of 2x, you get a turn, everything else stays as it is. Everybody gets a turn. All right, now, second derivative, h double prime. Okay, we go through again. We have a product and a chain rule. So, okay, derivative of the first. Derivative of 2x is 2 times the second, leave it alone, plus 2x times the derivative of the second. Derivative of f of 2x, f prime of 2x times 2. Don't forget the chain rule. Okay, so that's, I'm going to use the parentheses, just emphasize that's the first piece. Plus, now let's do the second piece. The derivative of the first, 2x, times everything else. So that's f prime of 2x and times 2. Plus, and I'm running out of space, I'll wrap around here, the derivative of the second. Right? We have the x squared, don't forget that. Derivative of the first times the second, plus the first times the derivative of the second. Derivative of f prime, f double prime. And then there's going to be chain rule, another 2. There's already a 2, and so that makes it 4. All right, so there we go. Or if we clean it up a little bit, not that we have to, but we might as well, we end up with 2 times f of 2x. Then we'll have a 4x f prime of 2x, another 4x f prime of 2x. Not a coincidence that those look the same. So that gives us an 8x f prime of 2x. And then we have this last piece, which is going to be plus 4x squared f double prime of 2x. Whew! Okay, with all of that out of the way, we're now ready to plug in 1. So, h double prime of 1 is 2 times f of 2 plus 8 f prime of 2 plus 4 f double prime of 2. It's really easy to plug in 1. Essentially just say, the x's go away, because they're 1s. So, we know these values. So we have 2 times negative 2 plus 8 times 1 plus 4 times 3, which makes this negative 4 plus 8 plus 12. And that gives us a grand total of 16. Is that one of our options? Yes. All right. So that's C. Okay. And there we go. And that's the end of our multiple choice. We're doing great. Plenty of time. We've only used about a third of our time. So that means we're going to have a luxurious time when it comes to doing our workout problems. All right, let's go and start. Number 7. Use the limit definition of the derivative to find the derivative of the function f of x equals the square root of 4x plus 1 at the point x equals 2. Now, there's not a lot of things that you can always predict about a calculus exam, but when it comes to the first exam for Calculus 1, you can predict that this will be a question where it says, use the limit definition. And you're like, okay, I know it's coming. I know it's coming. So you say, well, how do we do it? And the answer is, we knew it was coming. And it's right here. Here's the limit definition of the derivative. It's given to us. And so we don't have to memorize it. We know how to find it, right? That's all we need. And so we say, okay. Now notice, this is at a particular point, so we don't have to find it everywhere. And so we say, okay, so we're looking for f prime of 2. So step 1, always start here. You say, okay, I'm looking for f prime of 2, and I'm just going to literally just copy this, except wherever I see x, I'm going to put it 2. And if I do that, I just got a point. I'm like, yes! Now, I'm going to go for more than 1 point on this problem, but I'm going to get at least my point. Okay? There's our limit definition. From here, there's going to be a combination of two things. Making sure we understand how to use our notation and algebra. So, first off, understanding notation. What is f of 2 plus h? So we have a rule. We say, look, f of x is square root 4x plus 1, which means f of anything, doesn't have to be just x, is 4 times whatever you plug in plus 1. And use your parentheses generously. And so that's oftentimes when people lose points, it's because their parenthesis game is not tight. You want to have a really good parenthesis game. So I'm going to now say, look, what is f of 2 plus h? It is the square root of 4 times, use my parentheses to my advantage, 2 plus h, and then plus 1, minus f of 2, square root of 4 times 2 plus 1, all over h. Okay, so we've now done do you know how to plug stuff in? A lot of people miss it here. And if they miss it here, then everything after this is going to become more and more hopeless. So make sure you got your parentheses game locked down. You're like, there is not anything I'm going to miss when it comes to that. All right, now let's clean it up. And there's only a handful of things that might happen algebraically at this point. One of them involves square roots. You have to deal with square roots, you have to deal with fractions, you have to deal with polynomials. Right? Those are your three things that usually you have to work with. I'm going to distribute here. You get 8 plus 1, which makes this a 9. And then there's a 4 times h. So remember the 4 distributes. And then here minus square root 8 plus 1 is 9. Square root of 9. I guess we could have written that as a 3. Okay, all of that over h. How do you deal with square roots? So the answer is we want to get rid of them. And you're like, oh, yes, square it. And it's like, well, we can't quite square things. That's not how math works. You have to follow certain rules. We have to leave it something that's equivalent to what we started with. So we say, okay, how can we leave it equivalent to what we started with and somehow get some squaring going on? So here's where, when you have square roots, you do what's called multiply by a well-chosen one. In particular, multiply by the conjugate. And so this takes advantage of something called the difference of squares, right? So if you have a plus b times a minus b, then you get a squared minus b squared. So here's your a minus b, a plus b. And so what you're left with is you have limit as h goes to 0, your a squared, 9 plus 4h, minus your b squared, minus 9. Now downstairs, we're not going to expand. We only multiply where it helps us. 9 plus 4h plus square root of 9. Now the good news, because we multiply top and bottom by the same thing, multiplied by 1, we're still the same. But the other good thing is that this is not 0. Yes, that's going to be helpful. Now we are going to go a little bit slowly here, just so that they don't mark us down for anything. We're going to mark that the 9's cancel. Okay, limit as h goes to 0. 4h over h times square root 9 plus 4h plus square root of 9. And then we're going to say, hey, you know what? The h's cancel. Cool. So we're going to say this is the limit as h goes to 0 of 4 over square root 9 plus 4h plus square root of 9. And now we say, okay, why did we do all this work? I probably should have been talking about that before we got started. Why do all this work? Well, the thing here is that whenever you start out, you always start out with 0 over 0. You always start out with 0 over 0. That's the challenge with derivatives. So you don't want 0 over 0. So we're trying to get to a place where we don't have 0 over 0. We want cancellation. And in particular, our real secret goal is we're trying to cancel these h's. So that's what we were trying to get to, a place where we could cancel h's. That cancels the 0 over 0. And now we can plug in. All right, so this equals, and here we're just going to make a note, plug in h equals 0. Upstairs we get 4. Downstairs we get square root of 9 plus square root of 9. Well, that's really 3 plus 3, so that's 4 over 6, which is 2 over 3. And that's our answer. Okay, a few other notes. Make sure your notation is right. They will be careful and making sure you get it right. And when I say they're being careful, they're going to be very particular. So you want to make sure you write your limits at every stage until you actually evaluate, and then you don't want to write limits anymore. Right? So put limits when you need them and don't when you're done with them. So So you're going to have a lot of limits that you need to write down. Be careful with notation, because that's going to cost you if you don't. Not only will it cost you points now, but it will cost you understanding later, because notation is important. I don't think, we celebrate that enough in mathematics, but notation matters. All right, well, that was, as I said, this is the most predictable problem you're going to see. You know it's coming, be prepared, and then you get the points. All right, so I guess the rest of it's going to be unpredictable. Let's see what we have. Number 8. Suppose the tangent line to y equals x squared plus 1 at x equals a passes through the point 2, 1. Find all such a. Okay, well, interesting problem. What do we see? We have x squared plus 1. Now, that's actually not too hard to draw, because we know x squared is our generic parabola. The plus 1, we're going up, up, up with the parabola. Okay, so we're going to come up. So here's our parabola. Y equals x squared plus 1. And then we have this point, 2, 1. And so here's our point at x equals 2, y equals 1. And what do we want? Well, we want our tangent line at our point passes through there. Okay. All right. Well, I see one tangent line that does it, right? You can almost like, hey, look, just go right there. Woohoo! We found one. All right. Well, that was just eyeballing it, but that doesn't mean that's the only one. So be careful. Don't just trust your picture, even if it's a great picture. What's going on? So how do you approach problems like this? And here's how I like to think of it. It says, well, I'm after a particular tangent line. So what I'm going to do is I'm going to make all the tangent lines, right? Not just one, but all of them. And you're like, we can do that? Absolutely we can. So what do you need to make a line? You need a point and a slope. And in particular, we recall that our tangent line at x equals a is y is equal to f of a plus f prime of a times x minus a. Now you're like, oh my gosh, what if I don't recall it? It's right here. This is your tangent line. Y equals f of a plus f prime of a times x minus a. It's on the formula sheet. It's like they want us to know things because they want us to know things. Okay, so, all right. So now what we'll do here is this x squared plus 1, this is our f of x. And I'm going to make a note, f prime of x is 2x. All right, now with this, we say, okay, so our tangent line looks like y is equal to f of a squared plus 1, plus f prime of a, which would be 2a, times x minus a. All right, so this is the generic tangent line. What do we know? Well, we want a tangent line. It has to pass through this point. So we know, okay, if we plug in this 2, 1, this is an x, y. So we say plug in 2 for x, and we should get 1 for y. All right. Well, let's see what that becomes. And what we'll get is, as long as that's satisfied, right, that's a tangent line that contains that point. And if it's not satisfied, it doesn't contain that point. So we're going to get a formula for a. We get the formula 1 is equal to a squared plus 1 plus 2a times minus a. And now we're like, wow, cool, neato. Well, maybe we don't use the word neato. That sounds really 50-ish. 50s, we're not, we've got to say modern thing, like, oh yeah, I don't know modern thing. I should learn that. Okay, but anyways, let's clean this up. Here we have 2a times minus a, that's minus 2a squared. And, okay, so what do we get? Well, the 1's cancel. All right, well, that's good. And, oh, whoops. I forgot the 2. I was like, wait a second, something's not right. I forgot to put the 2 in. So, double check. As the great philosophers have said, you should check yourself before you wreck yourself. And, okay, all right, back to our regularly scheduled solving problem. All right, so we get 1 equals a squared plus 1 plus 4a minus 2a squared. The 1's cancel. That's nice. So we get 0 is equal to 4a minus a squared. Right? A squared minus 2a squared makes minus a squared. Well, that's equal to a times 4 minus a. And that leads us to two solutions. A equals 0 or a equals 4. And so we have found all such a. By the way, we knew about a equals 0. That was this one. A equals 4 says you have to come up way up there, and they're going to be coming down. But you can't even see it. So that's why, you have to be careful. When you only draw a little piece of the picture, you might be missing solutions. So, but there we go. Ah, beautiful, beautiful. And we made it through another workout problem. We're doing great. We have plenty of time. So, find dy dx, where y equals x squared plus x tangent x over 1 plus 2e to the 3x. Do not simplify your answer. Okay, so we're going to follow their instructions and not simplify our answer. Now, what do we have going on here? There's a couple of things. We have a quotient, because we see a fraction. We have a product, x times tangent x. And we have a chain, 3x inside of e. Now the good news is we have the quotient rule, a product rule, the chain rule, all of them written down. So if in doubt, we can just sit here and stare at it until it makes sense. And I like to think of these types of problems as onion problems, in that it has layers. And I say, okay, so what's the outermost thing? The outermost thing is the quotient. So I say, okay, so I'm going to start by applying the quotient rule first. And then as I move in, I have, as my layers, I have the x tangent x, and I also have this 2e to the 3x. And don't forget, we also have, very conveniently, the derivative of tangent. We have the derivative of the exponential function. We even have the derivative of e to the something x. So we barely have to do a chain rule. And so there's a wealth of information here. It's just a matter of, can we use what we have? All right, so here we go. Slowly. Now, quotient rule says take the bottom times the derivative of the top minus the top times the derivative of the bottom. So most people remember this as low d high minus high d low over low squared. So however you choose to remember it, you always have the formula sheet. Make sure you apply it. So we have dy dx. I'm going to do this in 2 steps. So it's going to be the top times the root of the bottom. Sorry, I said that backward. It's going to be the bottom times the root of the top. I can follow this. So low d high minus high d low. All over low squared. Okay, which is, all right, copying down. I just copy that first part down. 1 plus 2 e to the 3x. And then say, hey, if I'm taking derivative of a sum, take the derivative of the each pieces. All right, derivative of x squared is 2x. Now, this is one of my layers. X tangent x. Product rule. I can take the derivative of the first, which is 1, times tangent x, plus the first x, times the derivative of tangent, which is secant squared. Okay, so that's that part, minus x squared plus x tangent of x, times the derivative of this part. Derivative of 1 is 0. And then here, chain rule, or just say, hey, derivative of e to something x, that something comes down. So the point here is that you can bring a 3 down. There's already 2, so that makes 6 e to the 3x. And leave the bottom as is. And there we go. That's it. What's being tested on this? Let's be clear what's being tested on here. We are being tested on, do we know our rules? And that's it. And almost every single exam, for Calc 1, has this type of problem. They're going to say, hey, here's this crazy function. You're going to need to know a combination of rules, the right order of applying them to get the derivative. Do you know your rules? So know your rules. But it's not just about knowing your rules. It's just saying, look, how do you apply them in concert with each other? And so this is sort of a matter of like, okay, do you understand how to put things together? And that's why I like to call these onion problems. There's layers, and the question is, okay, at which point do you apply which rule? So that's going to be a big, huge chunk of these problems. So pay attention. Know when to apply the rules. All right. We made it through that one. One more to go. And we have plenty of time. So let's enjoy it. So, number 10. An object is launched into the air at t equals 0 sec, I'm going to assume that means seconds, from a platform that is 5 feet, which I'm going to assume means feet, above the ground. The object's height in feet above the ground is given by this formula, minus 2t squared plus at plus 5, where t is greater than or equal to 0. All right. Now, part A. If A equals 3, how long after launch does the object hit the ground? Well, okay, so question, where's the ground? Well, the ground, that would be corresponding to a height of 0. So, what do we do? Well, we're really trying to say, when does s of t equal 0? Now, we're told if a equals 3. So we can put in minus 2t squared plus 3t plus 5 equals 0. And, okay, can we solve? And we just need to find one value of t where this is true. And, well, hopefully there's more than one. Now, if you're clever, you could probably say something like, hey, I think this probably factors, and it does. Factors as t plus 1 and minus 2t plus 5. Now, where does that come from? Minus 2t squared plus 5t minus 2t is 3t and plus 5. Now, you're probably thinking like, I'm not sure where that came from. Well, we'll talk about an alternative. And so you get what? T equals negative 1. And here you get, because right, we set each part equal to 0. And here you get 2t equals 5, or t equals 5/2. Now, -1 doesn't make sense because we think of time moving forward. We wouldn't say, oh, it hit the ground 1 second before we even started things, right? Because we were told t has to be greater than or equal to 0. So we say, aha, this must be our answer. So we get t equals 5/2 seconds. Now, what if you didn't see how to factor that? No worries, because what can we do? We can always throw in the quadratic formula, and spoiler alert, it's in the formula sheet. -b plus minus square root of b squared minus 4ac all over 2a. Yeah, so if you couldn't see the factoring, then you could say, okay, t equals -b plus or minus square root b squared minus 4ac all over 2a. Well, this becomes -3 plus or minus square root, and you get here, well, you're going to get plus, right, because there's two minus signs making a plus. There's 9 plus 40, that's 49, all over -4. And so this becomes -3 plus or minus 7 over -4. And you're going to want the -3 minus 7 over -4, because if you do that, what will you get? You'll get your 5/2. -3 plus 7 over -4 will get you your -1. So that's another way you could have done it. But the important thing is to say, you hit the ground, height is 0. Solve for t. And, okay, so that's part A. Part B says, okay, well now we're changing it. No longer is a equal 3, it's a equals 12. Okay, so if a equals 12, when does the object reach its maximum height? Okay, so we have s of t equals -2t squared plus at plus 5. But we said, hey, wait a second, a is 12. So -2t squared plus 12t plus 5. Now let's reason. What's going on? So we're starting at a height 5. We're initially going to go up, and then we're going to go down, and we're going to hit the ground. And, okay, so this is our time t. What's true initially? We're going up. Okay, so how do we use that? Well, if we're going up, our height is increasing, right? The derivative is positive. If we're going down, our derivative is negative. So our sweet spot, our maximum, here we say, oh, s prime is positive, we're going up. S prime is negative, we're going down. So our sweet spot, our max, happens to be when our derivative is 0. So we're using calculus tools. You can do all this, by the way, without calculus. It's you do some completing the square. But let's use our calculus tool. So we want s prime of t, which is -4t plus 12, to be equal to 0. And we say, okay, so that says 4t needs to equal 12, or that says t equals 3. So it's at 3 seconds. All right, so that's the answer for part B. For part C, suppose now a is 1,000. Find the object's acceleration at t equals 2 seconds. Include your units. Okay, so we now know its location. That's s of t. That's -2t squared. And this time I'll remember to write the a right away, plus 1,000 t, and then plus 5. Okay, now we want to find object's acceleration at t equals 2. This is position. If we take one derivative, we get s prime of t, which would be what? Well, that's -4t plus 1,000. And this right here is velocity. Okay, so that's our rate at which we're moving. Now, it's a little different than speed because we could be positive or negative. So it says, or like we have a little bit of an idea of an orientation. Are you going forward or backwards? S double prime, well, that's -4 and just -4. And that's acceleration. Okay, so we're after acceleration. All right, so we come into our double prime and we plug in 2. And what do we get out? We get out -4. In fact, it doesn't matter what time we plug in, we're going to get out -4. So the answer is -4. Now notice it did say include units. All right. So how do you figure out your units? Well, you start with your units for the original, which was S. So this was in feet. Now, when you take a derivative, what happens? You keep your units of your original, and then you divide by the units of your input. So our original was feet, and then our input is time. So that's feet per second. For the second derivative, we start with feet per second, and then what do? Well, we're going to take feet per second, which we say that, oh, that's really feet per second squared. It's feet per second, but feet per second squared. And that's the answer to part C. And there we go. That's the final problem. Oh, we made it. And not only did we make it, my goodness, we have plenty of time. So we can go back, double check, catch mistakes. It's useful to catch mistakes. And, it's not, don't be embarrassed about making mistakes. We learn from them. But also don't try to make too many of them. And if you're going to make mistakes, try to make interesting new mistakes that'll help you learn and prepare. So we had a great time. What an interesting collection of problems. I'm not sure what your test will be like, but I do know that by practicing problems that were on old exams, you get a sense of what might be on the future, and you get better. The way you grow is through practice. Do problems. So I'm glad you came, and I'm glad you joined me. Good luck on your exam. I hope it goes well. I want you to succeed. Your teachers want you to succeed. We think you're wonderful. All right. I hope I get to see you again.